Hello students, this is the continuation of our discussion on data and development analysis and its applications in economic research. Um, in this screencast, I will first be discussing the primal and dual parts of an optimization problem, and then I will show you that how primal of a linear programming model is converted into its dual, and why we may need this. See that in our microeconomics course, we had seen utility maximization problem, and if you recall that we had drawn a budget constraint, and then subject to this budget constraint we were trying to maximize utility, and so we obtained a particular combination, for example of x and y, to indicate that these were the optimal quantities of good 1 and good 2 respectively, and this was the utility maximization problem. See that and there was another aspect of this problem, and it was that the minimization of expenditures, that the same utility could have been attained with different expenditures expenditure levels, and see that it was because of this reason that we had seen side by side to the utility maximization problem the expenditure minimization problem. And in that discussion we had seen that whether you are looking for the combination of the goods x and y which will maximize utility subject to the budget constraint, or the combination of x and y which will uh, be allowing you to attain a given level of utility with minimum expenditures, will give you the same answer in terms of x and y. So whether you are minimizing expenditure subject to the utility constraint, or you are maximizing utility subject to the expenditure constraint, see that outcome remains the same: x1 units of good 1 good x and y1 units of good y. In this context, our utility maximization is what that is known as the primal, and expenditure minimization could be seen as its dual. And we have a general statement saying that to every uh, primal of an optimization problem, there exists a dual to that problem. So primal could be written in terms of the objective function and the constraint function. Similarly, its dual could also be written in terms of the objective function and the constraint function. In our utility maximization problem, utility was the objective function, and that budget constraint was the constraint function. In expenditure minimization problem, which is dual of the utility maximization problem, we have minimization of expenditure as the objective function, and the constraint is the utility function. Exactly same type of things happen in the linear programming, where we are like dealing with the different constraints and an objective function, and see that here we have the objective function given in the form of this equation. Maximize z equal to 2x1 plus 3x2 plus 5xy, and that what we are saying is that this um, value is to be maximized value of z, which is depending upon these three variables x1, x2 and x3, is to be maximized over these three constraints. This is the first constraint, this is the second constraint, and this is the third constraint now we have here. And then these are the boundary, these are the restrictions that we are putting. I'm saying that the value uh, x1, x2 and x3 should be equal to greater than 0. This restriction will be making sense if we are assuming that x1 and x2 and x3 are the quantities which can only be positive or 0, and they cannot be negative. Like for example, quantities of goods consumed, or like for example, quantities of goods sold. So good quantity of good 1 sold equal to x1, quantity of good 2 sold equal to x2, quantity of good 3 sold equal to x3. Or for example, this may be something else which can have positive or 0 value but cannot have negative value. Whenever this is the case, we have to impose these restrictions or constraints that x1, x2 and x3 or anything else which is required to be so should be greater than or equal to 0. And see the constraints that we have. The other one is like the first one, x1 plus x2 minus x3 equal to greater than minus 5, and then I have minus 6x1 plus 7x2 minus 9x3 equal to less than 4, and so on. When solving for the maximization problem, remember one thing. In the context of linear programming, I am talking that all these constraints for maximization problems, all these constraints should be appearing in equal to or less than format. So every constraint individually should be having a sign equal to or less than. The second constraint is alright, where we have equal to less than 4. The third constraint is alright as well, where we have the sign of equality. The first constraint is not defined in this way. It is like saying that the left hand side is greater than or equal to the right hand side. And because in order to solve this maximization problem, we need to have the inequalities in the form of equal to or less than. We can do that by multiplying this first constraint by minus 1, and this is what that I have done here in this second set of equation, where I have put this objective function as it is, but then see that the first equation has been multiplied by minus 1, and so this inequality, which is being read as equal to greater than the right hand side, now becomes equal to less than the right hand side. The rest of the equations are same, nothing changing here. So whenever this is the case, this is the first thing that you need to do in the context of maximization problem when you are dealing with linear programming. Then the next step, which is needed to convert a maximization problem into its dual, which will be a minimization problem. So in order to do that, the first step is to write down the problem in the standard form, and this is something that we do by converting all the inequalities into equalities as far as the constraints are concerned. So see that first constraint was equal to less than 5, and in order to convert this first constraint into an equality, or this weak inequality into equality, we need to add something on the on the left hand side, because in this constraint originally what we are saying is that the left hand side could be less than the right hand side. We want to make sure that this is not happening, so this means that we have to add something, and so we have added s1 here in this equation, so that s1 must be greater than or equal to 0. And see that if this was originally an equality, then s1 will be equal to 0, but whenever this is less than 0, so s1 will be greater than 0. Similarly is true about s2. So see that in equation 2, because we had the possibility that s2, the left hand side could be less than the right hand side, so we have added a sort of variable here, a quantity representing a quantity s2, and we say that this s2 also has to be equal to or greater than 0. These are known as the slack variables, that if inequality is there, then this means that some slack is existing. We call them the slack variables. So this means that the slack variable plus rest of the equation must be equal to 5. Suppose that 5 was the capacity of some machine. So what this equation was originally saying was that this firm or the firm was using this machine either to the fullest extent, that is 5 units, or less than that, and whenever it is using the machine to the extent which is less than 5, to mean that there is a slack. So for example, if 4 is the left hand side, to this means that there is a slack of 1 unit under utilization. So this is the concept with which this term slack goes. Alright, once we have done that, we need to I myself prefer to add another step, and it is that I want to rewrite all the constraints and equation in a way that in every equation all the variables will be appearing. So see that here in the equation I have all the variables that are now existing in the system. X1, x2, x3 are the given variables, and also I have introduced s1 and s2, but because s1 and s2 is not a part of the objective function, so see that I have put 0 coefficient with s1 and s2, so the equation remains unchanged. Similarly, in this first constraint, see that as far as slab 1 is concerned, it could either be greater than 0 or it could be equal to 0. So its value, because it is associated with this constraint, its coefficient is equal to 1. Because S2 is representing the slack of the second constraint, so its coefficient here has been put to 0, so that it is like saying that S2 has nothing to do with the first constraint. Similarly is here, this because we are in the second constraint, I have put 0 as a coefficient of S1 as if it is not existing. And because H2 is slack relevant to the second equation, we therefore have 1 as a coefficient of H2 in this equation. Now as far as this equation is concerned, this must also be written in the same format. So we should be having actually x1 plus x2 plus 4x3. And this is something that I missed actually, and then because I want to have all the variables in every equations. So I put 0 times s1 plus 0 times s2 and this is equal to 10. So this should be this equation, the last constraint. See that the slack variables have been introduced only into the equations which are having weak inequalities. This third constraint, which was strictly equal on the left hand side and right hand side, we therefore have not introduced any slack here. So this is like a constraint that we cannot have less than of this facility. So that otherwise the objective will not be satisfied. So why I have done that is that now I have all these equations such that each equation, the equation of the objective function as well as all the constraint equations have all the variables with which we will be dealing into in this linear program. See that because we want to convert this actual problem, which is now the primal of the optimization problem, into its dual. So remember that dual will be in terms of minimization. So every maximization problem has a dual in terms of minimization, and every minimization problem has its dual defined as a maximization problem. Here we are because dealing with this constraint, um, so this maximization problem, so we need to convert this maximization problem into minimization problem. This is what that we are doing, and see that there are a few things that you need to keep in mind, and for this conversion of primal into dual, and it is that the number of equation in the primal, the number of variables in the primal, it is going to be equal to the number of constraints in the dual. So the first thing that you need to keep in mind is that let me write it here, that whenever there is a maximization problem, then the objective function, as an objective function, the maximization problem is primal. Let me write it down. Primal, and we have dual. Right. So maximization problem in hand, its dual will be a minimization problem, and that if we have a minimization problem, and then its dual will be maximization problem. This is the first thing that you need to keep in mind. The second thing is that the number of variables in primals, will be equal to the number of constraints in primals. Number of constraints. So in this example, see that we have 3 original variables and 2 slack variables. So 3 plus 2 equal to 5 variables. So this means that while primal is having 5 variables, so this means that the dual will be having 5 constraints. This is the second thing that you need to keep in mind when you are converting a primal into a dual. And then there is a third point that you need to remember, and it is that the number of constraints. So number of constraints in primal will be equal to the number of variables in dual. Number of variables in duals. This is something that you need to keep in mind. Now, the question is that why do we need to convert a primal into a dual? Well, the answer is that this conversion actually is a sort of a convenience that may work to your advantage whenever it is possible. See, in our case, in the original problem, we have five variables, and there are three constraints. So, if we convert the maximization problem into minimization problem, so see that number of constraints equals to 3 in the primal will become equal to the number of variables equal to 3 in the dual. So we will only have to solve for 3 variables, 3 unknowns. So because it is more convenient to solve for 3 unknowns rather than solving for 5 unknowns, so this is something that is like a convenience, and so we may want to do that sometimes. Sometimes there are maybe other reasons due to which we might want to convert a primal into dual. You could look into some operations research textbook to see that what are the advantages that might be available sometimes when you are wishing to convert your primal into dual. Um, See that um, in order to do this conversion, I have made this table. So this is something that is like the name of the variables that I have given to the dual problem y1, y2 and y3. I have made this table. Need not to be done, but it is like a sort of keep all the things in organized form. So it is for this reason that I prefer to work with this type of table. In this table, see that y1 is y1, y2 and y3 are the variables that will appear in the dual problem, and then that this C is the constant. They are representing they are coefficients of the objective function. See that the first coefficient is 2, and it is appearing here in the last column as a first constant on the on the right hand side of the dual constraint. This second element is 3, and see that this is appearing here on the right hand side of the dual constraint. This is 5, and this is like 5 appearing on the right hand side of the dual constraint, and then the other two constraints are 0 and so on. This is the first step then in this table, that we look into the objective function, and the coefficients of the objective function in an ordered way appear in this last column. The second last column is having a sign of equal to greater than. Every minimization problem, remember, has to have equal to greater than sign. So when the problem of maximization has been converted into a problem of minimization, so we will have all the constraints in equal to or greater than form. And then see that I have written down all these constraints here. And the first, all these variables here. G actually is going to replace Z of maximization, So in minimization problem we will be writing minimize g, and then see that I have written down all these variables again in an ordered form. So see that in the last column we are having the coefficient of the first variable, and here is the first variable of the primal problem x1. In the last column we have this in the second row 3, the variable, the coefficient of the second variable x2, and so in this first column we are having x2 and so on. So in the ordered way, x1, x2, x3, the first variable, the second variable, the third variable in the objective function, the fourth variable in the objective function, and the fifth variable in the objective function. So this is done, and then see that as far as this first row is concerned, this first row, these 4, 5 and 10, see that where they are coming from. They are coming from the constraint. They are now the right hand side of the constraint. So first constraint is having a value equal to 5. Error. Okay. Let's suppose that, what can we do here? Let's suppose that this is our first constraint. This is our first constraint. So I'm making this first constraint. Assume that this is the first constraint and this is the second constraint. See that in the first constraint on the right hand side we have 4, so we have 4 here. This it becomes now the second constraint 5, so we have 5 here, and then the third constraint is having 10 on the right hand side, so we have 10. So this first row actually will be having the right hand side of these constraints, and then see that we will be able to write down the objective function, and this has been done here. That when we look into this equation, minimize g, and when we are saying that we need to minimize g, and see that we are saying that minimize g, which is equal to 4y1, where 4 is the right hand side of the first constraint, plus 5y2, where 5 is the right hand side of the second constraint, plus 10y3, where 10 is the right hand side of the third constraint. So this is one thing that you need to keep in mind, that the right hand sides of the constraints will be defining the coefficients of the dual variables. There are 3 dual variables, y1, y2, y3, and right hand side of the first constraint is defining the coefficient of the first dual variable. Right hand side of the second constraint defines the coefficient of the second dual variable, and right hand side of the third constraint define the coefficient of the third coefficient of the third dual variable. So this is something that has been done, and the same is like true for the constraint as well. The relevant row and column actually will be defining the coefficient of y1, y2 and y3. So this is the third row, and this then will be defining the first equation, constraint equation. So this -1, so this means that in the first constraint -1 will be the coefficient of y1, in the first constraint +7 will be the coefficient of y2, and this +1 will be the coefficient of y3, and that equal to greater than this 3, which is the coefficient of the second variable in the maximization problem. So see that when we do that, our equation becomes minus y1 uh, minus 6 y2 plus 1 times y3 equal to greater than 2. So this is our first dual constraint. Similarly, for the second dual constraint, we have minus y1, and because we have minus 1 here, rather here, and that this is your 7y2. So see that we have 7 in the y2 column against x2, and then we have 1 times y3, that in the y3 column in the second constraint row we have coefficient of y equal to 1 and equal to greater than the last column is saying that the equation will have a right hand side equal to 3. Then we have the third x3 constraint. See that in the x3 row I have plus 1, so y1 is having a coefficient of 1, minus 9 is the coefficient of y2, and plus 4 is the coefficient of y3, and we have equal to greater than 5 on the right hand side of this equation, and then we have y1 and y2 equal to greater than 0, and this is the job get done. So see that if you are systematic, you will be able to convert any primal into dual by writing down this table. You can do it directly as well, but then there are chances that your errors might be increasing. So what is the rule? The rule is that in the primal problem, whatever are the right hand sides of the constraints, they become the coefficients of the variables in the objective function of the dual problem. So the objective function of the dual is to minimize g, and see that 4, 5 and 10 were the right hand side of the constraints of the primal, and they have become the coefficient of the objective function of the dual. Similarly, we need to remember that the coefficients of the objective function in the primal will be becoming the right hand side of the constraints on the dual, and then we have already seen that how we have written down these values. Last one is this one, y1 or y2 greater than 0. See that if you look into the second last row here, so you have a coefficient of y1 equal to 1, and then rest of the coefficients are 0, and so we have y1 equal to greater than 0. So this is the equation saying y1 equal to greater than 0. And then the fifth row here is like saying that first column here is equal to 0. So y1 is having a 0 coefficient, y2 is having a coefficient equal to 1. So we have a coefficient equal to 1 as well of y2, and so we have y2. This equation becomes y2 equals to 0, and so we have y1 y2 equal to 0. Because there was no third constraint, so see that the restrictions are only being put on y1 and y2. There is nothing that we could so as far as y3 is concerned, y3 is a sort of unrestricted variable. Unrestricted in terms of sign means that it could be negative, it could be positive, it could be 0. So only this only two restrictions are here, and say that they have come out of the of this table. So remember that every row is to be used in this table to write down every equation in the dual. That every element is representing the coefficients of y1, y2 and y3 in the objective functions and the constraint function. So see that how many constraints we are having? 5. What are those constraints? This is the first one, this is the second one, third one, and then see that this is your these are your two other constraints, y1 equal to greater than 0 and y2 greater than equal to 0. So this is how we convert the primal into dual, and if you follow the same procedure, you will be able to convert this dual following same steps into primal back. So if you assume that this is the actual problem that you have been given, minimize G subject to these constraints, and then like you are asked to convert this minimization problem into its dual. So see that how many constraints you are having. You are having 3 plus these two constraints 5. So this means that the objective function will have 5 variables. Similarly, like there are um, 3 constraints. So there will be 3 variables. Let's now turn to the discussion on data envelopment analysis. See that we will continue this discussion with an example where there are 5 firms involved that we are constructing the ranking of, and that there are 2 outputs that are being produced by these firms using the 3 inputs. We will be using Y to denote the output vectors. So there are 2 outputs. So output 1 is y1, output 2 is y2, and then we put a subscript n here to indicate that this is the output vector of the nth firm. So like this. So the actual amount will be then y1n and y2n. So subscript, see that the first subscript is indexing the output, and the second subscript is indicating the firm. So if we are talking with respect to firm 1, so this will become y11, and this will be becoming y21, and so on. Similarly, we will be using x for denoting the input vectors. It is 3-dimension, and that n will be again indexing the firm in question. So this then is x1, x, that is the first input, x2 is the second input, and x3 is the third input, and that if we are talking in the context of firm 1, so the first input used by firm 1, and the second input used by firm 1, and then we have the third input used by firm 1. So there is something that is to be kept in mind. Then see that we have started this problem with maximization of the this number, which is, and so this is an index of output, and similarly this v1 x11 plus b2 x21 plus b3 x31 is an index of input. This system has been written by normalizing the um, denominator of the fractional program, that we had something that we had seen in our class discussion. So see that what we are saying is that for the first form we are writing this system, so maximizing this objective function subject to these constraints. The first constraint is the one which is associated with the normalization. So what we are saying is that we have to select the variables in a way that this left hand side becomes equal to 1 is like a constraint. Because it is a maximization problem, so we have all the inequalities in the form of equal to, less than, and then see that these are the rest of the equations with which you are familiar because of our class lectures. One thing that you need to keep in mind is that here we are maximizing this objective function over u and v. That is, u and v are the variables, remember, not x and y, because x and y actually are the data points. This is the output being produced by one output 1. This is the output of good 2 that is being produced by firm 1. This is the quantity of input 1 used by firm 1 and quantity of input 2 used by firm 1, quantity of input 3 used by firm 1. So this is the data that is available to us. What we are trying to find out are the optimal values of u1, u2. So these are our variables, remember, and y's and x's are the coefficients of these variables. So this is the linear programming problem for form 1, and then now we want to convert this maximization problem into its dual, and of course the dual of this problem will be to minimize and see that because there are these 6 constraints, first constraint, second constraint, third, fourth, fifth, and sixth. So because maximization problem is involving 6 constraints, so 6 constraints in the primer means 6 variables in the dual. So our dual will be having 6 variables in dual. So this is one thing that we know, and then we construct that table, but before that we look into this format, the way that I have transformed these equations into matrix form. Maximize this row vector multiplied by this column vector, so you will be able to get this objective function. And similarly, this is going to be your first constraint equal to 1, of course, and then the rest of the constraints are mentioned in terms of these products of this matrix along with this matrix, and this matrix along with this matrix, with minus sign around here. Let's see that if you open this system, you will be able to get back these equations which are written here. So first constraint has been written separately, and then the rest of the constraint have been written in. We assume that you should be able to like write it down by yourself. So because they assume that you have a knowledge of linear programming, so they don't mention it that how they have arrived at that system. So see that as far as this one is concerned, this equation could be written as u transpose times yn. And now you know the meaning of this, that this is your u1 and u2, and yn actually is y1, y2, and so if it is y1, from 1 to we will be having y11 and y21. So they write it like this. This is the nth firm. So writing the system for nth firm, u transpose multiplied by the output vector for the nth firm. So this is to be maximized. So we write maximize this subject to the constraint, and now see that we'll be writing this constraint again in the form of vectors and matrices. So vt is rather the transpose of the vectors v1, v2, v3, and then we multiply by xn. So xn actually is x11, x21, x31 for firm 1, x12, x22, x32 for firm 2, and so on. And then if you look into this system, this is again the transpose of u, vector u, and this is what that we get, and this is something that is representing yn. So I write it here yn, and then we have this minus v transpose, and this is xn, and then what we are saying is that this is for equal to less than 0, and this is something that is true for, you have to mention n equal to 1 to up till n capital. Alright, so we have 5 firms, so n will be equal to 1 to up till 5. So this is how this system actually is mentioned in the textbook, or sometimes in the research papers when you are reading them for literature review. For example, here we have to have one as well. What else? Actually, the last thing you have to add here is that u and v should be equal to greater than 0. So vector u should either be equal to 0 or greater than 0. Same is true with v. So this is how we write this system in a compact form, the way it appears in the textbooks and in the research papers. Now we want to convert this system into its dual, and I have already shown you that this means that the dual will be a minimization problem carrying 6 variables. So these 6 variables we are naming them as theta, lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5. So these are our dual variables, and then see that in order to obtain the dual, we first need to write down the entire system in the form of equations, which will ensure that every equation is having all the variables. So see that this is what that I have done here. Maximize this. We have the objective function. Maximize u1 y11 plus u2 y21. This was the amount, say the um, first input, because the objective function does not involve any inputs, so x11 actually is equal to 0. Similarly, x21 is equal to 0 here. X31 is also equal to 0. Then, because there were 5 constraints with the equal to less than signs, so we have introduced 5 slacks. So this is the slack for the first inequality constraint, this one. We are not going to introduce any slack for this equation because this is strictly equal to 1. But all the rest of the constraints are having equal to less than sign, indicating the possibility of slack. So we have introduced these 5 slacks from S1, S2, S3, S4, and S5. But see that they do not they actually are not a part of the objective function, and so we have put coefficient equal to 0, so that they will be equal to 0 for this objective function. Then the first constraint with respect to which we are maximizing is it does not contain any of output, neither output 1 nor output 2. So u1 multiplied by 0 plus u2 multiplied by 0, but it contains inputs. So this weight variable will be having a coefficient x11. This weight variable v2 is having a coefficient equal to x21, and similarly v3 is having a coefficient x31. And because this is an strict inequality, this slack is associated with the first constraint, so its coefficient is 0 here. This slack is associated with second constraint, its coefficient is 0 here. Third constraint, coefficient 0. Fourth constraint, coefficient 0, and so on. So see that this first constraint is having all the slack variables as well. So we have all the variables in our system in this equation as well as in all the other equations. Let me show you the other one. So see that u1 y11. So u1 is the variable and that y1 is the data point. How many units of good 1 being produced by from 1. u2 is the second variable, and that y21 is the output being produced by from 1 of good 2. And see that minus v1 is the variable, and x11 is the output being produced by, sorry, input being used by from 1 for similarly x21 is the input being used by from 1, second input being used by from 1, third input being used by from 1, and so on. And here we have see that S1 is not having a coefficient equal to 0, it is actually having a coefficient equal to 1 because it appears in constraint 1, and the rest of the slack variables are having value equal to 0, so that they will be disappearing actually later on. So similarly is true about the other equations as well. The thing that you need to keep in mind is that see that because v1 is our variable, the coefficient actually is minus x11, v2 is our variable, the coefficient actually is equal to minus x21 and so on. So this is the system that is to be used then to write the table that we had seen earlier, and this is what that I have done. See that the 6 dual variables have been indicated in this first row of this table. Theta, lambda 1, lambda 2, lambda 3, lambda 4, lambda 5. Then we have all the signs of equal to, greater than here, equal to, greater than here, and so on. And so let me put this sign equal to, greater than, and given that this is true for all these constraints. Now see this the way we have filled this table. We are each row will be representing the row in the dual, and that each row of the dual will be obtained by multiplying the corresponding variable in the first row with the coefficient which is existing in the corresponding column, like here. So for example, when we look into and then side by side see that where this row is coming from, 1 0 0 0 0 0. This is coming from the from the right hand side of the system. See, 1 0 0 0 0 0. So the entire column on the right hand side appears in this table in the form of row 1 0 0 0 0 0. Similarly, look into the left hand side. What are the coefficients of u1? The coefficients of u1 actually are 0, y11, y12, y13, y14, y15, and see that what happens here. In the second row we have 0, y11, y12, y13, y14, y15. So each column in this system now is appearing in this table. So this is going to be the first row in that table that we have seen, and similarly this is going to be the second row and this table, and then the third row will be like minus x11, minus x12, minus x13, minus x14, and minus x15. So see that the third row is like having starting from x11y, because see that in this column first element is positive x11, second element is minus x11, third element is minus x12, and so on. And so we have in this see that x11 is positive, then minus here as well, minus here. And then because we are writing down the minimization program, so the equation must be in the form of equal to and greater than 0, and here it is equal to 0. So because this is what that is happening in this system, this is like equal to 0. So we then write all these equations in this form, and our job is done. Now write down the program, the dual equation. So if I want to write down the equation of g, so it should be equal to these variables multiplied by the coefficient. G is in the first row, so I will be multiplying each variable by the corresponding coefficient. So when I will do that, so it will be like g is equal to theta times 1 plus lambda 1 times 0 plus lambda 2 times 0, and so on. And because all other elements will become equal to 0, and I will be having minimize G, or the way they write in text, minimize theta. And we are minimizing theta over these lambdas, remember. Then we start writing the constraints. So the first constraint that we want to write it down is see that theta multiplied by, now we are writing down the first constraint, theta multiplied by 0, lambda 1 multiplied by y11 lambda 2 multiplied by y12 lambda 3 multiplied by y13. And so this is what that I have done here. Minimize theta subject to the constraint lambda 1 multiplied by y11. The first element is this thing. See that um, theta multiplied by 0 is equal to 0. Then lambda 1 multiplied by y11. So 0 plus y11 times lambda plus y12 times lambda plus y13 times lambda 3 plus y14 times lambda 4 plus y15 times lambda 5. And then we have on the right hand side of this row equal to greater than y11. And if I take this y11 on the left hand side, this will be becoming minus y11, and on the right hand side we will be having a value equal to 0. So this is what that I have done here. I have brought this y11 from right hand side to the left hand side, so I have this minus, and then see that on the right hand side we are left with 0, and this construction I have already explained to you. Let's look into this second equation, the same. Now this will be the equation of y12, and see that theta multiplied by 0 is equal to 0. Lambda 1 multiplied by y21, lambda 2 multiplied by y22, lambda 3 multiplied by y23, and so on. And so we have, and also we have here, see that on the right hand side y21, we take this on the left hand side, it will be becoming minus y21, and so we have this second equation written here, minus y21 plus lambda 1 y21 plus lambda 2 y22 up till lambda 5 y25 equal to greater than 0. Let's do one more equation, and that is for the inputs. See that when we go back and we look into this row, coefficient multiplied by the variable, so theta multiplied by x11, and then lambda multiplied by minus x1, lambda multiplied by minus x12, lambda 3 multiplied by minus x13, lambda 4 multiplied by minus x14, and this is something of greater than equal to 0. So this is your this third constraint, theta multiplied by x11, and then we have minus lambda 1 multiplied by x11, and so on, and equal to greater than 0. So these are the constraints that we have first 5 constraints, and then we have the rest of the constraints. For S1, see that we have 0 multiplied by theta 1, 1 multiplied by lambda 1, 0, 0, 0, 0. So what we will be getting here is that lambda 1 will be equal to greater than 0. Look into the S2 line. S2 row is like 0 multiplied by theta, 0 multiplied by lambda 1, 1 multiplied by lambda 1, 0 multiplied by lambda 2, and so on. And sorry, 0 multiplied by theta, 0 multiplied by lambda 1, 1 multiplied by lambda 2, 0 multiplied by lambda 3, 0 multiplied by lambda 4, 0 multiplied by lambda 5 equal to greater than 0. And so we will be getting lambda 2 equal to greater than 0, and so on up till lambda 5. So lambda 5 will also be equal to greater than 0. So in total, see, then we have these 10 constraints. Why? Because we had these 10 variables in the objective function and in the system. Like, for example, what are those variables? We have a variable u1, we have a variable u2 in the original um, problem, v2 and v3, and then we have from s1 to s5 the artificial variable, you may call them. So there is something like having 10 variables or 10 constraints, and we are able to see that this actually has happened. These are the first 5 constraints, and then 5 constraints are here: lambda 1 equal to greater than 0, lambda 2 equal to greater than 0, and so on. So this is the dual of the maximization problem, and then we want to write this system in compact form and see that how I am going to do this is as follows: minimize theta. Theta is a scalar. It is scalar, and then see that I am first writing down this thing. So this is like a vector of output being produced by PAM1, and it is in minus. So I can write it as minus yn. N can be 1, 2, 3, 4. Yn. I'm writing it for general. And then plus I have here plus, and um, then see that if I write this as y, capital Y, and multiply it by lambda. So what is your y? Your y, capital Y. So your capital Y actually is equal to this matrix y11, y12, y13, y14, and y15, and y21, y22, y23, y24, y25, and then see that this is your y, and then I can have like a vector lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5, and see that if I find the product of these two, so I will be able to get these two equations, and see that this is like 2 is to 5, and this vector is 5 is to 1, and so this is something that is like conformable for multiplication, and that the product will have 2 rows and 1 column, and we have 2 rows and 1 column. So 0, 0 are the 2 rows, and so we will be having 1 column. So this is the first part that now I have indicated. So we have written this up till this part, the system. Here is this one, equal to or greater than 0. So equal to or greater than 0. So this is this part. Then let me erase this thing so that we are able to clear space to write down the rest of the system. So you could see that then the part that is below this system is like I'm going to have this first column here. See rest of the equations. I can write it as 3 times theta times xn you know what xn is. N is going to go from 1 to 5 plus this is the rest of the part. Sorry, this is minus. I'm taking minus out. So this is minus here, and then I have x lambda, where x is x, the matrix x11, x12, x13, like here we had. And so what we are saying is that this should also be equal to greater than 0. So this is equal to and greater than 0. And then finally we need to put the restriction that we had found when we were like writing down um, the the dual, and it was that lambda has to be equal to greater than 0. Lambda is the vector, you know. So minimize theta subject to this set of constraints. Definitely you need to write n equal to 1 to 5. And this is the last thing that we want to mention. So this is the way the system is reported in the research papers as well as in the textbooks, and this is how they arrive at this system. Now one more thing that you need to keep in mind is that this is sort of CCR model, and that the CCR model actually assumes a constant returns to scale. So this is assuming constant returns to scale, and this is the property of CCR model of DEA, Carnes, Cooper and Rhodes. And that this means that in this model it is being assumed that long run average cost actually is flat like this, parallel to x-axis. So if I have average cost long run plotted along the vertical axis, and say output along the horizontal axis for any commodity, the CCR model actually says that average cost will be like this. Constant returns to scales means that average cost, long run average cost remains constant. So there one thing that you need to keep in mind. But then see that this is not the only model that we have. There is another one that is known as BCC, Banker, Carnes and Cooper. They wrote that model to allow for variable returns to scales, and our next step is to see that model, investigate that model. So let's try to do that. So before turning to the BCC rather model, I want to correct one error that I feel that I have committed here in this system, because we have already introduced the slack variables. So this means that all these should be in equality form, so this should be equal to 0. Similarly, this should be equal to 0, and so on. So this is one typo that I observed towards the end of this section, and I hope that you will be able to correct it when you are writing down your own notes. So going back to the end of the discussion that we were having, I have now write down the equations for the basic CCR model, which is this one. So this is something that we have already seen, where we are minimizing theta and subject to these constraints. this is the linear program for the nth firm, and this means that we will be running down all these programs for n equal to 1 to 2 up till n, whatever is the number of n. Like I mentioned earlier, that this CCR model assumes constant returns to scales, and by assuming constant returns to scales, actually it assumes what is known as the scale efficiency. Remember that decision-making unit is said to be scale efficient if its size of operation is optimal, in the sense that any reduction in the size of operation will render the DMU scale inefficient. This is something that we can show by drawing this long run, so let me do it here, long run average cost. It will allow you to understand the meaning of scale efficiency more precisely. Suppose that this is your long run average cost, and this is your output, and this is your long run average cost along the vertical axis, and this is Q star, where long run average cost is at its minimum. Then this level of output Q star is said to be scale efficient. So scale efficiency is associated with minimum of is associated with the level of output, which gives us the minimum of long run average cost. See that when we were studying microeconomics courses, we had constructed a relationship between returns to scales and the shape of the long run average cost. See that increasing returns to scale means that long run average cost is falling, and that decreasing returns to scale is like long run average cost is rising. That Q star is the output level at which long run average cost is at its minimum. So this means that if I multiply long run average cost by Q star, I will be getting the long run total cost, and so it is like saying that the Q star is the level of output at which we will be having minimum long run average cost, and so we will be having per unit cost at the lowest, and so the total cost for producing Q star is at its minimum as well. And see that if we are producing any level of output less than Q star, this means average cost is more than the minimum, and it is taken as an indication of the fact that the output level that is now being produced is less than the output level at which the average cost is at its minimum. It is in this sense that then Q dash is said to be a level of output which is associated with scale inefficiency. Similarly, if you find yourself here in the upward sloping portion of the long run average cost, then this associated level of output Q double dash here is said to be scale inefficient, because you are like producing a level of output at this level of output at per unit cost which is more than the minimum. So this is the concept of scale efficiency, or scale inefficiency. Q star is scale efficient optimal scale of operation. It is often known as, and Q dash and Q double dash actually are the quantities or any quantity to the right hand side or left hand side of Q star is the quantity in this particular case where we say that scale inefficiency is existing. See that um, we have like written down this um, CCR system, and if we assume that there is only one output and one input, so then the total product curve will be linear in the CCR model, and that if we assume that the possibility of variable return to scale, then the total product curve will be like concave, having a concave shape like this, and so you can like see the difference between this CCR, and this is something that you will be getting BCC. So what actually the BCC model is doing is that if these are the data points, so see that BCC model actually is trying to envelop these data point with more closeness. So it is like becoming to see that this is the segment which is becoming closer to this observation, and so there is a possibility that the ranking in BCC of this outcome or data point will be better than the efficiency it's in ranking in CCR model. Let us see how it happens. Call this one as point P, and then take this point on the total product curve, call it PV, and take this point on this constant return to scale total product curve and call it PC, and then see that if we are having if we are having a CCR model, then the scale efficiency, sorry, the technical efficiency will be in terms of the distance of the point P from this vertical axis relative to points PC. So A times PC is this point divided by A times P is this distance of the inefficient outcome, and see that APC divided by AP is the technical efficiency. So what we are saying is that because this point P is not at the total product curve, so this means that it is producing the same level, given level of output with more inputs. So it's not making use of minimum input, and that because this point is on the total product curve, this is efficient. And see that as P keeps on coming closer and closer to this production total product curve, it becomes more and more efficient. Ultimately, if P coincides with PC, then this means that the efficiency ranking will become equal to 1. But then see that when we are talking with respect to the technical efficiency using the BCC total product curve, so then it will be equal to A times P of V divided by AP. And if you compare the CCR technical efficiency score with the BCC technical efficiency score, both have same denominator, but the numerator of BCC efficiency score is greater than the numerator of CCR efficiency score. Then this means that BCC efficiency score is greater than the CCR efficiency score. So this is one thing that you need to keep in mind while comparing the BCC and CCR model, that in BCC model what we are doing is that we are allowing for the variable returns to scale. See that in this range you have increasing returns to scale, and that in this range you have decreasing the returns to scale. So the BCC model actually allows for both increasing and decreasing returns to scale. This is one thing that you need to keep in mind. And then the other thing that you have to understand is that the BCC score of technical efficiency will either be equal to or greater than the CCR score of technical efficiency, and this graphical presentation actually makes it clear that why this will be the case. Let me give you another possibility, where suppose that we are like in place of at point P, suppose that we are here at point B. Let me take another pen, right, this one, at point B. So let's suppose that this is your point B, and then we want to ask the question that what is the efficiency score for this point, because this is not on the efficiency frontier, so this means that this is technically efficient. So the relevant point on the CCR total product curve is BC. So let us write it like this, BC, and that this is the image on the vertical axis. And now define the technical efficiency in the context of CCR. It will be equal to the distance ABC divided by the distance AB, and see that greater the distance AB, more will be the technical efficiency, or say more precisely, more will be the CCR technical efficiency. If in place of CCR model we use the BCC model, then see that the image, the point B will be benchmarked against point say BV. So let us call this point BV, which is on the total product curve associated with the BCC model. And then in this case we have a BV divided by AB, and this again is the technical efficiency score, which is greater than the CCR technical efficiency score, because both denominator are same, but ABV is greater than ABC. So this means that numerator is greater than this numerator, and so this BCC technical efficiency score should be greater than the CCR technical efficiency score. So this is one thing that you need to keep in mind when we are discussing the difference between BCC and CCR model. So we say that BCC model allows us to capture aspects of scale efficiency, and we'll see that how this happens. And this model actually imposes an additional restriction, and it is that a firm is benchmarked only with the firms which are similar in size. In the absence of such restrictions, as is the case in CCR model, there exists a possibility that a small firm might be benchmarked with a firm that is sufficiently larger in terms of scale of operation. So for the smaller firm, there is a possibility that it might be in the downward sloping portion of the long run average cost curve, and for the larger firm there is a possibility that it might even be on the rising portion of the long run average cost curve, or at the minimum of long run average cost curve because of optimal efficiency. And we really want to avoid such a situation. We want to see that firms of a particular firm is benchmarked against the firms which are similar in size, and this is something that BCC model is able to do by adding one more constraint into the original CCR model, and this is what that we have done here. See that these are the same things which were present in the CCR model. So same output equation, same input equation. This is the additional constraint. So CCR model plus this constraint makes it BCC variable returns to scale. And in this constraint, see that ET actually is the transpose of E, where E is a vector of 1. So E is a vector of 1. So I am like having 1, 1, 1, 1, 1 because I have 5 lambdas. So I will have 1, 2, 3, 4, 5 ones. And then if I take the transpose of it, and then I multiply it with the vector lambda. So see that what happens is, so I have lambda 1, lambda 2, lambda 3, lambda 4, and lambda 5. So this is this, and when I multiply these two, I get actually lambda 1 plus lambda 2 plus up till lambda 5, and you see that the right hand side is equal to 1, so that is equal to 1. So this is the additional constraint that the BCC variable return to scale model is having. Now, variable return to scale means that it has a portion of increasing returns to scale as well as a portion of decreasing returns to scale. So there is something, and of course the constant returns to scale. So all the three returns to scales are possible as far as this particular model is concerned. Let us now turn to the scale efficiency part. First thing to remember is that scale efficiency concept makes sense only if data reveals sufficient evidence about variable returns to scales. In this case, we compute both the CCR technical efficiency score and BCC technical efficiency score, and then we define the ratio of technical efficiency score CCR divided by the technical efficiency score BCC, and that is like a measure of technical scale efficiency. So I can write that scale efficiency um, will be equal to technical efficiency CCR divided by technical efficiency um, BCC. So, for example, in this graph, if B is the point under consideration, so see that BC ABC, distance ABC divided by distance AB is the technical efficiency score with CCR. So technical efficiency, no, sorry, scale efficiency is equal to um, distance ABC divided by AB, which is technical efficiency using the CCR model. And we divide this by the technical efficiency defined using the BCC model, and that is this distance BV divided by AB. So AB V divided by AB, and so AB is cancelled out, and we have scale efficiency um, equal to ABC divided by ABV. So this is the scale efficiency for point B, and see that this is going to be equal to or less than 1. You can also see from this formula another aspect, and it is as follows, that we first clean this thing so that we have some space. So see that this formula also tells us that technical efficiency uh, from CCR model actually is equal to technical efficiency using BCC times scale efficiency. So what this equation is saying, that if a variable return to scale is a realistic assumption, then the technical efficiency can be decomposed into these two components, and in this equation then this component actually is known as the pure technical efficiency component. So pure technical efficiency component, and then this is scale efficiency. So technical efficiency in the case of variable returns to scale is it can be decomposed into two parts: pure technical efficiency and scale efficiency. So this is one thing that you need to keep in mind, side by side the fact that whether you are talking in the context of technical efficiency or scale efficiency, these efficiency scores are bounded by 0 and 1, with 0 the lower bound and 1 being the upper bound. And if the score is equal to 1, then this means that the firm is efficient. I want to comment on this point C, that let's call it S. So see that what is happening at S is that we are having technical efficiency equal to the scale efficiency. So here scale efficiency is equal to 1, and technical efficiency is equal to 1 as well. So technical efficiency CCR actually is equal to technical efficiency BCC, which is equal to 1 in this case because this point is on the total product curve, multiplied by scale efficiency because this is something that is indicating that the variable that the total efficiency score, technical efficiency score are not different in CCR and BCC model. And this is what that is to be kept in mind, that scale efficiency will exist only if the technical efficiency score with CCR model is different from the technical efficiency score with BCC model. So this is the additional point that you need to keep in mind. The problem with this is that this approach allows us to conclude that the scale efficiency exists or it does not exist. If it exists, this formulation of BCC model where this additional constraint has been put does not allow us to see that whether the scale efficiency is because of decreasing returns to scale or whether it is because of increasing returns to scale. And if we really want to find out this thing, then we have to make a little adjustment in this variable return to scale model, and that adjustment is that this last constraint, in place of having equality, we convert it into weak inequality, and so we have a new model like this: minimize theta subject to the constraint that minus y and plus capital Y lambda equal to greater than 0 and so on, and see that everything else is same. The only thing is that we have a little bit tweaked this last constraint in terms of equal to less than sign rather than using the equal to sign. When this is done, then this variable return to scale model actually turns into what is known as the non-increasing returns to scale. Non-increasing returns to scale will have then two components: one constant returns to scale component and the other one decreasing returns to scale component. So these are the two components that are possible in this particular model, and see that this second graph actually is doing this thing. This is, let me first erase these items so that we are able to see it more clearly. So see that this is something that is telling us that this total product curve actually has two components. First is this linear component which is representing constant returns to scale, and then see we have this decreasing returns to scale component like this one. So this is the decreasing returns to scale component, and see that this adjustment allows for non-decreasing returns to scale, means that returns to scales are either decreasing or constant but not increasing. Using this model, the nature of the scale inefficiency for the firm can be determined by comparing the non-increasing returns to scale technical efficiency score with the BCC technical efficiency score. If non-increasing returns to scale technical efficiency score, that is, if the technical efficiency score computed on the basis of this model is equal to the BCC technical efficiency score, then we have decreasing returns to scale, and this means that the firm is actually operating beyond the optimal scale. In if they are unequal, so that if the score obtained from this non-increasing returns to scale is technical efficiency score, here is different from the BCC technical efficiency score. So this is technical efficiency score with non-increasing returns to scale. And what we are saying is that if this is not equal to the technical efficiency score using obtained using the BCC model, if this is the case, then this means that the firm is operating in the increasing returns to scale region. So this implies increasing returns to scale. Equality implies decreasing returns to scale, and inequality implies increasing returns to scale. So if you look into this long run average cost curve, see that we have increasing returns to scale here because long run average cost is falling, and this is decreasing returns to scale because long run average cost is rising. So if these scores are not equal, then this means that we have decreasing returns to scale, and if they are equal, then we have increasing returns to scale. Sorry, if they are unequal, then the firm is operating in increasing returns to scale, and if they are not equal, if they are equal, then the firm is operating in the range of decreasing returns to scale. So technical efficiency, uh, non-increasing returns to scale um, equals to technical efficiency uh, BCC model. If this is the case, then we have decreasing returns to scale. So there is something that is true about the returns to scale concept. So then remember that the deep software that you can obtain freely allows for all of these models, and you can easily obtain the score, technical efficiency score, scale efficiency scores, and so on. Now I am like finishing this component.